Oh, all right. Hi, everyone. So this is just going to be a quick video of something that we did in class, and it's about an introduction to continuity and what it means for a function to be continuous versus discontinuous. So I'll walk through the first 3 pages. We did them in class, and then the last 2 pages will be yours to complete as a sort of check for understanding or as an assignment. So my first question here is, has there ever been a time in your life when your weight in pounds was exactly the same as your height in inches? And why? So think about it, pause the video, really consider it. Keep in mind that when you're born, most people start around 7 pounds and like 19 inches. But just for the sake of this video and our time, I'll just go ahead and just talk about it. So if you start like 7 pounds and 19 inches, that means you're you begin life, most people do, with your weight less than our height. And then as we grow older, like most of us right now, if not all of us, I would say all of us, our weight eventually surpasses our height, like the number of your weight, the amount of your weight, ends up being larger than our height. So for example, if you have a 120-pound adult, and I don't know, what are most adults, like 5'7" maybe, which is 67 inches. This 120 is much larger than the 67. So if you start with your weight less than your height, and as we grow up, our weight eventually becomes larger than our height. Therefore, the answer here is yes. At some point, our weight and height have to be equal because we switch from being less than the height to being greater than our height. Our weight and switches from being less than the height to greater than the height. And the idea behind this is something that we're actually going to learn tomorrow. There will be a video sent out later this evening about it. And this all has to do with the idea of continuity. So since if our weight starts at 7 pounds and our height starts at 19 inches, that means if we end at 120 pounds, that means we will have a weight of 7 and then everything in between 7 and 120. Same with our height. We'll have a height of 19 and everywhere in between 19 to 67. Because these concepts are continuous. You know, I don't just skip a height at some point. I don't just suddenly jump from 5'2" to 5'4". You know, you have to have everything in between too because you grow. Your height and weight are continuous. So I'll let you decide how you want to explain your reasoning for this. I just talked a bunch. But in our own words or graphs, we talked today what it means for a function to be continuous. And there was a lot of talk of a function, you know, has to approach infinity or negative infinity as we go left or as we go right. You know, like the function has to go on forever. It can't just end. And then we eventually decided that a function is continuous if, here, I'll write this down. A function is continuous if there are no breaks, jumps. Oh, we used another word. Oh, like holes in the graph. That means you will not see stuff like this. Yeah, remember we've talked about graphs with a hole in the graph. This is called removable discontinuity. So this is not continuous. Or if we have a piecewise function that looks like this. this is not continuous because, we can't just draw this with one line. We'll talk more about more official definitions later. But this is basically like, yeah, you can draw the whole line without picking up your pencil. And now questions 3, 4, and 5, I did have students do on their own today. So, obviously, you can choose if you want to pause this video and do them on your own. We talked about them as a class, so I'll just do them here too. So I guess I actually already did this one, at least two. So let's sketch some graphs of at least 2 examples of functions that are not continuous. And I'll help you see maybe there are different ways that a function might not be continuous. And functions that are not continuous are called discontinuous. So let's see. I'll draw some graphs here, or some coordinate grids. I'll just do a few. Let's see. So we have removable continuity, which I already talked about. Removable discontinuity. There's a hole in the graph, or sometimes you define the point to be somewhere else like that. This is discontinuous at this point. Or you might have a piecewise function that goes up until here, and then we jump down to here. This is called jump discontinuity. And don't worry about writing this down. It's in a separate set of notes. This is just an intro activity. Oh, let's see. What else do we have? I'm actually just going to do 3. Let's see. Oh, there's infinite discontinuity. So it's like if you have an asymptote, let's just go ahead and say at 0, someone goes like this. And maybe this one goes like this. This is discontinuous at x equals 0 because we jump from this line to this line. So let's draw some more functions that are discontinuous at a certain point, x equals 3. We'll sketch 3 graphs to demonstrate the 3 different ways in which this function might be discontinuous. And then we're going to describe the discontinuity using limit statements. So I'll walk us through this. So we have a graph and a graph and a graph. Okay. Let's see, at x equals 3. Call this 3 for all of them. All right, number 1, there's a hole. You can have a hole in the graph. So let's just say we have a hole at x equals 3. Number 2, we can define a sort of jump function. So maybe we go up right here, but then right here we go like this. So this function is decreasing until we hit 3, and then we jump up, and then we're increasing. Or maybe 3 is an asymptote, and maybe this is a function. This goes towards infinity, but it approaches 3, and well, you could actually have this going either way. You can have this line go up like this, or down. I'll just have it go up. And x equals 3 is an asymptote. Okay. So now let's kind of discuss what's going on here using limit statements. So we're actually going to write down 3 things for each of these. We're going to find the limit as x approaches 3 from the left of these functions f of x, and the limit as x approaches 3 from the right of f of x. And finally, we're just going to find the value of f of 3 for each of these functions. So I'm just going to actually just go ahead and write this out for each of them, and then we'll talk about what all these values are. So the limit as x approaches 3 from the right of f of x, and f of 3. Okay. So let's take a look at this first graph. The limit as x approaches 3 from the left of this function. That means we're starting from the left and we go towards x equals 3. Oh, maybe I should define a value. Let's say that this value is 2. So from the left, as x approaches 3, y approaches 2. Well, how about from the right? All right, as x approaches 3 from the right side, y also approaches 2. So that means the limit as x approaches 3 is 2. So the limit does exist in this case. But check out f of 3. The value of f of 3, if this hole is at 3, this is undefined because this open circle means that that value is not included in this function right here. So that means this f of 3 does not exist. It's undefined. Okay, well, how about this second example? What's the limit as x approaches 3 from the left? I guess I should probably define these. Maybe this is at 1 and this one is at 2. Okay, so from the left, that means we're starting up at the left and we go toward x equals 3 and we approach 1. The y value we approach is 1. How about the limit as x approaches 3 from the right? That's what that little plus means, remember. The y value approaches 2. So hey, these two limits approach different values. Therefore, the limit as x approaches 3 does not exist. And let's see, f of 3 this time. So we use the closed circle because the closed circle is the value that's included. So f of 3 would equal 1. So in this case, our f of 3 is defined, but our limit as x approaches 3 does not exist. All right, let's take a look at this last one. The limit of f of x as x approaches 3 from the left is infinity. Y approaches infinity, and that's the same as we approach 3 from the right. And f of 3 does not exist. So this is another case. Oh, well, that works out. Another case where the limit actually does exist, but the value at the point x equals 3 does not exist. The y value does not exist. So maybe you can kind of see some patterns here. So in all of these theory examples, either f of 3 did not exist or the limit did not exist. And that's what it means for a function to be discontinuous. So we'll go ahead and define that right here. Describe using limit statements a function g of x that is continuous at x equals 3. That means the limit as x approaches 3 from the right of g of x equals the limit as x approaches 3 from the left of g of x. Therefore, the limit exists. And we'll call that limit value L. And it also has to be true that f of 3 equals L. That equals your limit. So these three things have to be true. The limit of g of x as x approaches 3 from the right has to approach L. And the limit as x approaches 3 from the left has to equal L as well. And f of 3 has to equal L. And if any of these three conditions fail, then your function is not continuous at that point. So now in general, a function f of x that is continuous at x equals a Okay, so that means three things have to happen. F of a is defined. The limit of f of x as x approaches a exists. So we need f of a to be defined. We need the limit to exist as x approaches a, and this limit has to equal f of a. So this limit of f of x as x approaches a has to equal f of a. And y'all, this is the formal definition of continuous. So if a function follows these three items, then that function is continuous. All right, and that was it. That's what we did today. And then, oh, I'll let you just do this on your own. What did we, okay, sorry, I forgot about this. So skills and facts that we learned today or recalled, we had to know how one-sided limits. Let's see, we learned about continuity, the definition of continuous. Problems 5 and 6 on the page before. We learned what it means for a function to be discontinuous. That means there's a break, there's a hole in the graph, there's a jump, the values of the function like jump. Yeah, and I'll let you add more if you find more things. Methods to determine if a function is continuous. Is continuous at a point. We did this in problem 6. So that's a method we can use to determine if a function is continuous at a point, if that function meets those 3 criteria at that point. And then concepts to understand. Well, we definitely have to have a good understanding of limits to be able to understand continuity. You also, students said today, you need to have an understanding of graphs, and you need to have a pretty good understanding of what functions look like or what the end behavior functions are, which is what we've been doing up until last week. So lots of background knowledge needed to understand continuity. But that's going to be it for this little video. The rest of this packet is yours to complete. So this is a practice. So just complete these problems. So look at this graph, identify the x values, which there are discontinuities. Yep, and so your job is just to complete pages 4 and 5, and then take some pictures of your work and submit them on Canvas. So that's it for this video. Please email me if anything is confusing or if you have any questions at all. All right?